These are the notes for 1-5. Today we're going to look at a review of exponent rules. So as we continue our warm-up into pre-calculus, we need to make sure that we are remembering what our exponent rules are and how to use them. So it says recall for any real number b, okay, if we have b to the power of n and n's a positive number, it's simply, b to the n. We're going to multiply b times itself n number of times. If b is equal to 0, if n is equal to 0, b to the power of 0, right? We know anything to the power of 0 is 1, except for 0. You can't raise 0 to the power of 0 and get 1. And then if b is being raised to a negative exponent, right, that is the same thing as 1 divided by b to the positive exponent. Remember, positive exponents are repeated multiplication. Negative exponents are repeated division. All right, let's look at some of our rules and a couple examples of each. So the first one we're starting out with here, right, we've got x to the power of m times x to the power of n. So when we have two factors here, right, they have the same base and we're multiplying, we are going to add our exponents. So it's like rewriting it with one base and adding the exponents together. So x to the power of 5 times x to the power of 3 is going to end up being x to the power of 5 plus 3, or x to the 8th power. Same thing here on example 2, x to the negative 4th power times x to the negative 2nd power, right? Doesn't matter, we can still take it here and rewrite it as negative 4 plus the negative 2nd power, which gives us x to the negative 6th. And typically we don't leave our exponents negative, so remember here, just one of our other exponent rules, right, that is the same thing as saying 1 over x to the positive 6th power. Second one, we have the opposite here. We have x to the power of m now divided by x to the power of n. Right, in which case, if we multiplied and we added the exponents, now division, we are going to subtract the exponents. So looking here, we have x to the 3rd power divided by x to the 5th power, which is the same thing as saying x to the 3 minus 5 power, which is x to the negative 2nd power, and then we can rewrite that as 1 over x to the positive 2nd power. Example 2, x to the negative 2nd power divided by x to the 4th power is like saying x to the negative 2 minus 4th power, or x to the negative 6th power, which we can rewrite as 1 over x to the positive 6th power. The next example we have is when we take a power and raise it to a power. So we have x raised to the power of m, and then we're going to raise that to another power. What we get there is x will now be raised to the power of m times n, right? We're going to multiply those exponents. So we'll see here x to the negative 3rd power, we're raising it to the 4th power. That's the same thing as saying x to the negative 3 times 4th power, which is x to the negative 12th power. And if we wanted to rewrite with a positive exponent, that would be 1 over x to the 12th power. Doesn't matter if we have, fractions in our exponents too, right? They're still just numbers. So the next one we have x to the 1/2 power, and then that's being raised to the 8th power. This is still the same thing as saying x to the 1/2 times 8th power. Half of 8 is 4, so we get x to the 4th power. All right. Next one here is when we have a product raised to a power. So we have the product x times y, and it's being raised to the power of n. All that's going to happen here is each factor will end up getting its own power, right? So we're going to raise each factor to the power of n. So we have x to the power of n times y to the power of n. So as we look at our example 1, we have 3 times x squared, and that whole thing is being raised to the third power. So this is the same thing as saying 3 to the third power times our x squared to the third power. And when we look to simplify each, we know 3 to the third power is 27. And we have x squared to the third power, right? We're just using our previous rule. We're going to raise a power to a power, so we're going to multiply. So we should get 27 times x to the 6th power. Same thing's true here. We have the product 5 times x, and it's being raised to the negative 1st power, which means that each factor gets its own exponent. So we have 5 to the negative 1st times x to the negative 1st, which really ends up being 1/5 times 1 over x, which gets us 1 over 5x. And last but not least, instead of having a product raised to a power, we have a quotient raised to a power. So when we take a fraction and we are raising to an exponent there, both the top and the bottom of our fraction, so our numerator and our denominator, both end up with their own exponents. So for instance here, if we have 1/5 to the third power, this is like saying 1 to the third power divided by 5 to the third power, and we can simplify each of those to get 1 over 125. And same thing's true here. We have on the next one there 2 over x to the third, and it's being raised to the negative 1st power. This is the same as having 2 to the negative 1st over x to the third to the negative 1st. Okay, and then we can end up moving things around as we need to here, right? We know that when we have a negative exponent, that's going to end up moving down from the numerator to the denominator, and the same thing from denominator to numerator if it's negative. So this is going to actually become a 2 to the positive 1st in the bottom, and on the top it becomes an x to the third to the 1st. And really, that's just saying x to the third over 2. Now with this one, you could also just look at it as, right, if we have a fraction here that's being raised to a negative exponent, in order to turn this exponent positive, we can simply take the reciprocal of our original fraction, and you'll see here we end up with x to the third over 2 to the positive 1st power, which gives us the exact same answer we just got when we did it the other way. All right, let's practice a few. First one we have here on the next slide, 2x to the 4th, and it's being raised to the negative 2nd power. So we can approach this from different ways, right? As long as you're applying your rules correctly there, you'll still get to the same answer. Me personally, when I see 2x to the 4th raised to the negative 2nd, I want to get rid of that negative exponent first. I'm getting rid of this first, which means I'm going to have to take it here and I can flip it over and make this 1 over 2x to the 4th raised to the positive 2nd power. So now we can just apply our exponent rules to the denominator. We've got 2 squared times x to the 4th squared, and so we've got 1 over 4, and then x to the 4th squared, which should give us x to the 8th. So 1 over 4x to the 8th is our answer. Looking at the next one, right, we have it raised to the negative 1st power. This might be one here where you'd like to take it and go ahead and apply the negative 1 to each of the factors inside. We could say we have 1/3 raised to the negative 1st power. We have m raised to the negative first power, and then we have n squared raised to the negative first power. So because we have a fraction in here and it's raised to the negative first power, we can simply take the reciprocal, and that would make it to the positive first power. Our m would become a 1 over m to the positive first power, and our n would become, our n squared would become 1 over n squared to the negative first power, to the positive first power, sorry about that. Okay, and then if we look to put it together, it's like saying 3 times 1 over m times 1 over n squared, or 3 over mn squared. Okay, now, is that the only way to get to the answer on that one? No. You could apply any of the other properties or rules there, and you should get to the same answer if you apply them correctly. All right, and then we have, for the next example, 3x to the third, and then it's being raised to the power of b. So again, I'm going to take each factor and apply the exponent to it. So that would give us a 3 to the power of b and an x to the third to the power of b. 3 to the power of b isn't really going to change much. That'll just be 3 to the power of b. And then we're going to apply our rule when we're raising a power to a power. We're going to multiply these two together. So we have x to the power of 3b. And that would be our answer on that one. Moving along, we have x to the power of the square root of 3, and then it's being raised to the power of the square root of 6. So again, we are raising a power to another power. So we can take this and we can apply our property here where we are going to multiply the two powers. So we have x to the power of the square root of 3 times the square root of 6, which should give us x to the power of the square root of 18. And we know that's the same thing as the square root of 9 times the square root of 2. So we can simplify this down and make this x to the power of 3 radical 2. (4x over 49 raised to the 1/2 power). Okay, so we have a quotient, right, or a fraction being raised to a power. Let's just take it on this one, and we can apply a 1/2 power to both the numerator and the denominator. And remember, the 1/2 power is like taking the square root. So we're taking the square root of the numerator, which is square root of 4x. And we have the square root of 49 on the bottom. And then if we take our squares, right, so the square root of 4 is 2, so we'd have 2 times the square root of x on the top. On the bottom, the square root of 49 is 7. So this is our answer. All right, almost finished here. We've got just a few more to just take a peek at. So you'll see here there's a math notes box in the next slide. It says, so far we have only used integer exponents. So sometimes fractions are used as exponents as well. This occurs most frequently in interest rate problems such as a car depreciating or an investment appreciating. The exponent must be a fraction in order to compound the interest more than once a year. And then it says, here's a notation associated with fractional exponents. And this is the one here we just need to remember that when we have something here, and I'm going to just write this a little bigger, right? If I have x raised to the power of m over n, remember this is power over root. Okay, so the numerator is like the power we're going to raise it to, and the root value is our denominator. So that's why you'll see here that when we've got x to the power of m over n, this is like saying x to the power of m, that's the numerator, and then we're going to take the nth root of that. And that can also be written as the nth root of x and then raised to the power of m. Both of those are equivalent. So let's evaluate some down below. We have 27 and it's raised to the 1/3 power, which means our power, right, is going to be 1. So the power we're raising to is 1, and the root, right, is the 3rd root. So we're going to take the 3rd root or cube root of 27 to the 1st. And we know the cube root of 27 should be 3, because 3 times 3 times 3 gives us 27. The second one, 4 to the 5/2 power. So we could write this one a couple ways. This one could be written as the square root of 4 to the 5th, or it could be written as the square root of 4, and then we're raising it to the 5th power. Okay, both of those could work there. However, if you were trying to do this without a calculator, when you look at it here, right, I don't really know what 4 to the 5th power is off the top of my head, so trying to do that and then take the square of it may be a little bit more challenging, where if I apply the root first, like in this second example, I could do that first, and then it might be easier to raise it to the 5th power, right? Because the square root of 4 is 2, and this is the same thing as saying 2 to the 5th power, which would end up giving us 32. Okay, we get the same answer on the top one. If you really wanted to do it, you could. You could say 4 to the 5th power is actually, if I do it on a calculator, it would be 1024. And then if you took the square root of 1024, you actually end up with 32 as well. Okay, which method would I go with? I would highly, highly, highly recommend to go with this one here, where we do the root first and then the power second. All right, jumping into the third one here, we have 1/16 to the -3/4 power. So something that jumps out at me here, right, is I have a base that's a fraction, and I know I have a negative exponent. So I'm going to get rid of that negative exponent by rewriting this as 16 now to the +3/4 power. Okay, so that's how we can get rid of that negative exponent. And that means we're going to be taking the 4th root of 16. So the 4th root of 16, and then I'm going to raise that to the 3rd power. Well, the 4th root of 16, right, what times itself gives us, 4 times gives us 16, that would be 2. And then 2 to the 3rd power is going to give us 8. And that would be our answer. All right, and on to the last slide here. So we're going to change it up a little bit. We're going to just talk about solving equations. Okay, and these ones are just a little different than some of the ones we've been practicing. So the first one, we have the cube root of 3x minus 7, and it equals 2. So first thing to realize here, right, is we have just our grouping symbol and what's inside of it. There's nothing else happening here. So we already have the cube root of something isolated. So we can actually take it and undo the cube root by raising that side to the 3rd power. But if we do it on the left, we also have to do it on the other side. So we're going to do it on the right. So these will cancel, leaving us with 3x minus 7. And then 2 to the 3rd power is 8. And now it's pretty basic. We can just add our 7 to each side. We've got 3x is equal to 15, so x equals 5. Just a quick check here, right? Cube root of 3 times 5 minus 7 should equal 2. That's going to be a 15. 15 minus 7 would be 8. And the cube root of 8 is 2, so we know it checks out that our answer is correct. Last one, we have the quantity of x plus 2 raised to the power of 1.5, or 3/2, and that equals 8. So remember, if we want to try to isolate this x plus 2, we want it to be to the first power. We want to turn this into the first power. So in order to do that, let's raise it to another power. And if I raise a power to a power, remember, I'm going to multiply. So what I'm thinking about here is, what power could I raise this to so that when I multiply this times this, it gives me 1. And if you think about it in that case there, right, it would be the reciprocal. So I'm going to raise it to the 2/3 power. But if I do that on this side, I also need to do it on the other side of the equation. So here we would have x plus 2 to the power of 3/2 times 2/3 equals 8 to the 2/3 power. Well, 3/2 times 2/3 is going to give us 6/6, which is just 1. So this is like x plus 2 to the first power, which we don't need to put the parentheses and list the 1 as the exponent there. And then 8 to the 2/3 power, right, that's going to be the same thing as saying the cube root of 8 squared. And we know the cube root of 8 is 2, and 2 squared is going to give us 4. So we're going to go ahead and leave that as 4. And then finish solving for x. We end up with x is equal to 2. And if we really want to check it, we could take it and plug it in over here. We're going to say 2 plus 2 to the 3/2 power should equal 8. 2 plus 2 is 4. So 4 to the 3/2 power is equal to 8. So we'll take the square root of 4 and then raise it to the 3rd power. Square root of 4 is 2, and 2 to the 3rd power is 8. So you'll see here we get 8 equals 8, and we can feel confident that we got it right. That's all I got for you for this section. So this is section 1-5. If you have additional questions, please reach out and see me in class.